Okay. Bismillahirrahmanirrahim. So last time we have looked at the substitution reaction of halogenoalkanes with hydroxide ions, and the source of hydroxide ions can be from sodium hydroxide or potassium hydroxide. Halogenoalkanes undergo a reaction called nucleophilic substitution, but there's more specific mechanism, the SN1 and SN2. The next type of, well, it's still the same substitution reaction, but using a different nucleophile now. The nucleophile is the cyanide ions. Cyanide ions is made up of carbon with a triple bond attached to nitrogen, and there's a negative charge. The lone pair actually comes from carbon, not from nitrogen. Okay, so cyanide ions can be supplied from potassium cyanide or sometimes sodium cyanide. Okay, so the potassium and the sodium will not get involved in the reaction. It's just there as a counter ion. And another condition is that this potassium cyanide or sodium cyanide has to be dissolved in ethanol. It is not aqueous. Okay, so you will see sometimes in bracket, instead of writing it down as AQ, which stands for aqueous, we write it down as ETH, okay, which means that it is dissolved in ethanol. And the other condition is for it to be heated under reflux. So I've already explained to you how a reflux works. Basically, it's a setup so that your products will not escape into the air, and that whenever you have a gas product or a vapor, once it passes through the cold condenser, it will turn into a liquid and fall back into the reaction flask. Okay, so what happens here is that if I were to just show you the displayed formula of this compound, which is your bromoethane. Okay, so what happens is that your bromoethane will be replaced by the cyanide ion. So potassium will exist as K+, cyanide ion will exist as Cn-. Okay, so then your product will be the bromine atom will be replaced with your cyanide ion, okay, which then it will be called, so if you notice in the product, you have 1, 2, 3 carbon compared to in the initial starting material, you only have 2 carbon. Okay, so your functional group here is called a nitrile. So you see this nitrile, and to name this, you have to count the number of carbon, including the carbon of the cyanide. So the carbon chain has now extended to 1 additional carbon. Okay, so starting from 2 carbon and you'll end up with 3. This is called a prop because there are 3 carbons, propane nitrile. Okay, or called sometimes it's pronounced as propan nitrile, but there is an E there, propane nitrile. Okay, and the other products would be your Br- that you have lost from bromoethane, and of course your potassium ion that was from potassium cyanide. Okay, so that potassium ion is just to counteract any anions in the equation. Okay, so that is how substitution happens. But in order to show how the movement of electrons during this reaction, we have to draw the mechanism. Okay, and as you all know, mechanisms, there are two types of mechanism. Okay, so this reaction is actually a great reaction if you want to extend your starting material with one additional carbon atom. Okay, so cyanide ions will add one carbon atom to whatever starting materials you have. Okay, so we jump straight to the mechanism. SN1 mechanism would be for tertiary halogenoalkanes. Okay, so I'm going to choose, again, just a simple halogenoalkane. Okay, so you can copy as we go along. Okay, because this is something that you already know what to do. Okay, so SN1 mechanism means only one species is reacting or is involved in the first step. So that means your nucleophile is not attacking yet, right? So when we draw your mechanism, don't forget any dipoles that needs to be present. Any charges, dipoles, lone pairs, these are all crucial. So the first step is the breaking of the carbon-bromine bond, because bromine has a higher electronegativity than carbon, which results in the formation of a carbocation, which is a carbon with 3 bonds and a positive charge. Okay, so that bromine will become a bromide ion because it has gained the electrons from the CBr bond. Next, only in the second step, you will get your nucleophile attacking. And in this case, your nucleophile is the cyanide ions. So C triple bond N with a negative charge. The lone pair is the one that will be donated to the positive carbon. So your product will be a nitrile. Okay, so you notice that this positive carbon will combine with a negative species. So you will lose the charge automatically. Okay, positive and negative charge, they form a bond, they become neutral. So the product is a nitrile, so don't worry about naming this nitrile because it is a tertiary nitrile. You wouldn't be looking at nitrile as a functional group, so don't worry about the name. Okay, but I will teach you how to name nitrile that comes from primary halogenoalkanes. Okay, please let me know when you're done copying this. Then we can move on to the next one. So just remind you again that there is an additional carbon. Initially, you have 1, 2, 3, 4 carbon. And in the product, you have 1, 2, 3, 4, 5 carbon, because the carbon from the cyanide ions will be counted. And later on, this nitrile functional group will be transformed into a more functional molecule. Okay, so your cyanide part of the nitrile can be turned into a carboxylic acid. And from carboxylic acid, you can do so many things with it. Okay, are we ready to move on? Okay, right. Next will be the SN2 mechanism. So SN2 would be for a primary halogenoalkanes. So again, the simplest one that we can use is a bromoethane. That means a bromine with 2 carbon. Okay, so the 2 in SN2 suggests that in the first step, there are 2 species. Okay, so the first species is the halogenoalkane, and the other species would have to be the nucleophile. So the nucleophile comes attacking in the first step, which is the slow, or what we call the rate determining step, which is not of your concern right now. Okay, so before we start drawing arrows, we have to make sure that all our dipoles, all our lone pairs, any charges must be there. Okay, so sorry, it's not the hydroxide ion. It should be the cyanide ion. C triple bond N. Okay, with a negative charge. So the lone pair from the carbon will attack the slightly positive carbon. Maybe I should draw it like that. Okay, and then of course the carbon cannot have 5 bonds, so one of the original bonds have to break, and it is usually the carbon halogen bonds that will break. All the other carbons, carbon hydrogen, carbon carbon, will not break. Okay, so next we go into a transition state. This transition state, if you still remember, is where you form an intermediate with showing the bond that is about to break and the bond that is about to form. So that's C triple bond N. Don't forget your negative charge. Okay, and sometimes this is drawn as that square bracket to show that it is an intermediate. And then you don't have to do anything in this stage because that's just showing the bonds being formed or the bonds being broken, and then you just go straight to your product, where your bromine atom will leave your halogenoalkane to become bromide with a lone pair, and your product is now your nitrile. Please take note that you no longer have the negative charge. Okay, it's because in your final product, it should be a neutral molecule. So this one is your propane nitrile because it has 3 carbons, prop, and this is called a bromoethane because it has 2 carbon. Okay, when you're done, please let me know. Okay, great. Thank you, Ridwan. The next, okay, so that's just naming nitrile. So I will not worry about that. Okay, the next type of substitution is with ammonia as our nucleophile. Okay, now this is an example where your nucleophile is not charged. So ammonia, NH3, but you do know that because ammonia is in group 15, so there are 5 electrons in the outermost shell, 3 of it is already being used to form a bond with hydrogen. So that means nitrogen has a pair of electrons that are not used in bonding. So this pair of electrons can be donated, and because of that, ammonia becomes a nucleophile. So nucleophile is lone pair donor. Okay, so what happens is that, again, ammonia needs to be dissolved in ethanol, right? Not aqueous. So it's NH3 in bracket ethanol. If you write down NH3 aqueous, it's wrong. The reason why we don't want to use aqueous for cyanide ions or for ammonia is because aqueous is water. Water is also a nucleophile. Okay, so you do not want to have water in your reaction mixture. Okay, it has to be in excess. I'll explain to you later on why you need excess ammonia. The condition is to be heated under pressure in a sealed container. That means your setup, your apparatus needs to be airtight. The reason for this is because a few things. You do not want the products or even the reactants to evaporate, and also high pressure could increase the rate of reaction. Okay, right. So what happens is that when you have a bromoalkane, so in this case it's a bromoethane, you add ammonia, NH3, to form what we call an amine. So your bromine will be replaced by ammonia. However, ammonia has 3 hydrogens, correct? But when it forms a bond to the carbon of the halogenoalkane, of the original halogenoalkane, you cannot have 3 hydrogens. Otherwise, the nitrogen would have 4 bonds, and that would not give a neutral molecule. Yes, nitrogen can form 4 bonds in the form of ammonium ion, NH4+, but we do not want a molecule, a product with a positive charge. In order to get a stable product, we want a neutral product, okay? So the only way to make nitrogen to only have 3 bonds is by losing one of the hydrogens. So that's why in the product you see that there are only 2 hydrogens, because the other bond is to form a new bond with carbon. And this functional group is called an amine. It's a primary amine. Naming it, you just count the number of carbon. So that's eth, 2 carbon, ethyl, amine. So the NH2 part is the amine part, and this is the ethyl part. Okay. It is very important that the ammonia is in excess as the product of the nucleophilic substitution reaction. The ethylamine can act as a nucleophile and attack another bromoethane to form secondary amine, which is diethylamine. Okay, so this is the reaction. I forgot to include the lone pair on the nitrogen. So that lone pair is the one that will be donated, or the one that will be used to form a bond with the carbon. Okay, now in the product ethylamine, same thing. Nitrogen is group 5, group 15. It should have 5 outermost electrons. So 1, 2, 3, 4, and 5. Okay, so there is actually a lone pair on nitrogen. As long as that nitrogen has a lone pair, it can become a nucleophile. Okay, there is no rule saying that ethylamine cannot be a nucleophile because ethylamine still has its lone pair, right? You may argue, but the lone pair has been donated, has been used to be formed a bond with carbon. Well, remember the hydrogen that we lost? That nitrogen-hydrogen bond being broken, the bond in that, sorry, the electrons in that bond is used to restore the lone pair that was lost. Okay, so we'll see. You'll see when we look at the mechanisms. Okay, so I'll move on to the next one, SN1 mechanism. So SN1 will be a tertiary. Okay, so bear in mind now, even though I use a halogenoalkane, bromoalkane in general for my example, this also works with chloro or iodo. Okay, so fluoro not so much covered in your syllabus. Okay, the reason is because carbon-fluorine bond is a strong bond. Okay, as usual, you need to include all the dipoles, all the charges. So for now, SN1, there's only one species involved in the first step. So I should not have my nucleophile attacking in this first step, right? It's just my halogenoalkane. So the first step would have to be to break that carbon-bromine bond. Okay, so I break that carbon-bromine bond, I form a carbocation, CH3, with a positive charge because my bromine has taken or fully owned the electron pair from the bond. Okay, so then the next step is where my nucleophile comes in, and my nucleophile is an NH3. Okay, so do I have space? Okay, right. So what happens is that the NH3, specifically the nitrogen, because that's the supply or the source of my lone pair, will attack the positive carbon, which is a carbocation. Okay, so this is the only difference, right? Please take note. This carbon with everything else in the molecule stays unchanged, and then H3. Okay, when this nitrogen, a neutral molecule, donates that lone pair to the carbon, the nitrogen now becomes positive. Okay, the carbon already gained electrons, so the positive charge has been cancelled out by the electrons that it gains here. Okay, so carbon is positive, right? But then it receives electrons, so that bond, that charge cancel out. Positive and negative cancel out. But now the problem is with nitrogen. Nitrogen forms 4 bonds. So it becomes a positive charge. Okay, so this is not the final product that we want. As I said just now, usually the final product, we want it to be a neutral molecule, a neutral compound. So what happens here is that in order to cancel out this positive charge, the nitrogen, one of the nitrogen-hydrogen bond has to be broken. Okay, so I'll show you just the one below lah. Okay, so the bond from this nitrogen-hydrogen bond will be donated to that nitrogen so that it develops a negative charge and it cancels out the positive charge. Okay, so let's see what happens. Nitrogen-hydrogen bond breaks. both the electrons go to that nitrogen. So this is how the lone pair of the nitrogen is restored. Nitrogen with hydrogen, you lose that positive charge, but now you have a lone pair of electrons. And it is this lone pair of electrons that can become a nucleophile. So that's why your amine products can become a nucleophile. Okay, so please copy this down. Please let me know when you are done, okay? Okay. The product is the primary amine. Yes, that's right. Okay. So just add on to your notes that this molecule can act as a nucleophile. So that's why the condition says that you must have excess ammonia. So if you have a lot of ammonia, this amine will not be able to attack your halogenoalkane. So it will be a competition. Okay, the one that is present in a large amount will win the competition. So both of these molecules, ammonia and your primary amine, will compete to fight to attack your halogenoalkanes. Okay, so if we use a lot of ammonia in excess, ammonia will win the competition and this amine will not be able to attack your halogenoalkanes. Okay, the next example is SN2, bromopropane. So bromopropane is just, with 3 carbon. And because it is an SN2, the attack will come in the first stage. Or we say that there are 2 species appearing in the first step. Okay, so that's your NH3. Make sure your charges, your dipoles, your lone pairs are all drawn. So the lone pair will be donated to the slightly positive carbon. The carbon-bromine bond has to break. So you form a transition state, same thing. 3 carbon. So the rest of the molecule stays unchanged. It's just there in the background. The most important thing is this bond forming and the bond that is breaking, Br. Okay, and then usually it's drawn as with a square bracket over there. Okay, the next step is when you form the bond already, so I'm trying to save space. Your ammonia will now form the new bond with carbon, which it will develop a positive charge. Your bromine becomes bromide ion. And the last step here, that's not the final product yet. The last step here is to lose that positive charge on nitrogen. Okay, the only way to lose that positive charge on nitrogen is to break one of the nitrogen hydrogen bonds and donate its electron pairs to that nitrogen. So you form it's getting smaller and smaller because I try to draw everything in one line. So then you get a nitrogen with only 3 bonds and 1 lone pair. That lone pair came from the NH bond. Okay, so this is called a propylamine. Propylamine can act as a nucleophile. Same thing, if you don't want propylamine to attack your halogenoalkanes, you have to have your ammonia in excess. Okay, prepare your ammonia in big amounts so that any amines that you form in the reaction will not be able to attack your halogenoalkanes because it's a competition between the one with the bigger number and the one that is present in small amounts. Okay, so that is all for today. I'll let you copy this down. Is there any question before